So when we talk about the grounding issues in GIS, we are at an advantage because GIS is inherently safe to use. All the life paths are inside the enclosure, and the enclosure in the first place is a grounded metal enclosure. So we don't really have any life paths, access to life paths from outside. Of course, there are the bushings to air terminals from inside to outside. There are bushings which connect to the outside. Apart from that, the possibility of accidental contact is minimal. What we have to remember is that in case of a GIS, the disadvantage is that we don't have a large area over which it is spread, and therefore we do not have the multiple points, the extended network of transmission lines and earthen wires and grounding rods, everything coming together, and each of these points earthed provides us, in case of air transmission lines, it provides us a very extended grounding system, and that makes it easier to ground and safer. Because of the nature of GIS, this is not possible. However, we should still try to ensure that the GIS installation is grounded at multiple points. So we use a multi-point grounding system. That means we have short grounding conductors through which the GIS is connected all along its route at multiple points. It is earthed individually. And of course, the entire enclosure is connected together. So these are all multiple paths to ground. So these will provide parallel paths to the GIS main ground bus or the GIS grounding mesh. So you have multiple points of contact from the GIS enclosure to the GIS grounding mesh. Each module is electrically bonded either so there are different modules, and each of these modules are standalone prefabricated, and they are connected end to end either through flange connections or through external shunts. So this is like in continuous enclosure. So after the connection, all these modules connect as a single enclosure. So therefore, if you have any currents which are flowing through the enclosure path, they will flow through the entire enclosure path. So we have the possibility of enclosure currents flowing during normal operation as well as under fault conditions. And therefore, when you design the GIS return current conductors, you have to remember that currents will be returning through the return conductors, through the flanges and the shunts, and the design should be such that each of these paths taken together are designed for the full return current even under the worst fault conditions without exceeding the conductor's thermal and mechanical limits. So you need to make sure that there is all these currents can flow through all these multiple paths. The other concern that we have with GIS, which we do not have in air insulated substation, is that of greenhouse warming. SF6 is a greenhouse gas. Greenhouse gases, when they exist in the upper portion of the atmosphere, they tend to reflect the rays of the sun. The sun's rays enter the atmosphere, and from the earth they're reflected back. And when you have a lot of greenhouse gases, they tend to send back the sun's rays back into the earth, and as a result there is an overall increase in global temperature. So we have what is called global warming. Greenhouse gases contribute to global warming. Now the largest greenhouse gas, the greenhouse gas that is most detrimental to the Earth's ecosystem is of course carbon dioxide, and it is being generated by, all kinds of, even when we breathe out, we generate carbon dioxide. So if you compare to carbon dioxide, SF6 will have very little contribution in global warming because it is produced in very small quantities. If you consider the amount of CO2 that is being produced worldwide and the amount of SF6 that is being released to the atmosphere worldwide is very low. However, even very small quantities of SF6 has a high global warming potential. They heat to very high temperatures, and therefore, even if you have very small amounts released to the atmosphere, the impact can be much higher than even larger quantities of SF6. Another concern is that SF6 has a very high half-life. That means small traces of SF6 once released to the atmosphere can continue to have half-lives greater than 3,000 years. So once you have done it, it will be there. And there are no natural means of reduction of SF6. Carbon dioxide, there are natural means of reduction. SF6 does not have any natural means of reduction. So which means that even though we will be releasing very small quantities of SF6, that is going to be of potential danger. And therefore, the high voltage industry is under considerable pressure to control, limit the usage of SF6, and to make sure that when you use SF6, not even the slightest amount is released to the atmosphere. Unfortunately, even though there is a lot of research going on, we still do not have a viable alternative to SF6, which has the same kind of high dielectric breakdown strength or has equivalent arc quenching properties. So we don't really have an alternative. There are various alternatives which have been tried, for example, SF6 mixed with other inert gases, nitrogen and other inert gases, but we are still not in a position to give up on SF6. Another important thing is the pure SF6 is not toxic, so it's not a problem. But when you have discharges, when you have the gas in operation for a long time, there might be a situation where the gas will decompose, and some of the byproducts of this gas can be toxic. They can result in toxic gaseous and or solid decomposition products during high temperature or during electrical discharges, and that is a problem. So these are the safety issues that we need to keep in mind when we opt for GIS in lieu of AIS. So GIS monitoring has to be done very carefully, because since everything is prefabricated, since everything is enclosed, and since we don't even feel the need to do any servicing or maintenance over the initial periods, we have to make sure that monitoring is done. And the most important GIS monitoring is the monitoring of the gas. The first thing that we need to make sure is that there is always enough gas inside the enclosure, so that the dielectric breakdown strength that we are counting upon is available, and the arc quenching capabilities that is available. So enough gas has to be there. That's the first thing that has to be ensured. And for that, we have some kind of gas density monitoring. Apart from that, from other monitoring that will of course take place, a very important and very extensive monitoring that we need to do in case of GIS is partial discharge monitoring. Now, I did mention that GIS SF6 has a higher dielectric breakdown strength. However, SF6 is also very prone to charge accumulation. So it's considered to be a brittle gas, in the sense that whenever you have local field enhancement, local discharges are very likely to happen. And therefore, PD monitoring is that's an advantage, because PD monitoring will give us an idea about what is happening inside. We have a problem in GIS that we do not have access to what is happening inside, and PD gives us a good idea of any kinds of hazards, any kind of insulation, health deterioration that might be taking place. So extensive PD monitoring is done in GIS in order to be able to monitor the health of the system. So what are the reasons that cause PD inside gas insulated substations? We've already discussed this earlier, and it's quite obvious that the most important source for partial discharges are the metallic particles. The metallic particles acquire charge, and when they acquire charge, they're accelerated by the applied electric field, and this will cause the particles to bounce on the enclosure. So they have this lift off, these hopping excursions, they bounce off and they fall again. And when that happens, they generate PD, and the PD will generate both acoustic signals as well as electrical signals on the enclosure. If there is also a possibility that there might be some particles which may be sticking to the insulator surface, either because of static charge, or because of there is any kind of grease, or because of manufacturing defect. And so they're not hopping around, but they cause local field intensification. And over time, this local field intensification around these fixed particles can cause surface tracking to happen, treeing might happen, and ultimate failure of the insulator might happen. The partial discharges which are associated with fixed particles embedded in insulators is very low magnitude PD is observed. And in the early stages, they're very low, difficult to detect. Only when they go on to a situation where they're already hazardous, then the signals increase and we may be able to detect them. However, the movement due to particles which cause PD on the enclosure surface can be detected with better ease. Then we have floating components. As I said, that there are many components inside the GIS enclosure. For example, one of them is shields. We use shields for electric stress grading because, for example, when we have the spacers, along the spacers, there are points where you have a connection between the insulator, the metal electrode, metal conductor, as well as the SF6 gas. So three different materials come together at a single point, and this is called the triple junction. And it can be seen, and it also can be calculated, that these are the regions where you have very high field intensification and PD can occur. And in order to prevent that, we might provide some kind of shields so that the electric stress can be controlled. Now, when you have shields, these are metallic components. These shields do kind of equalize the stress, but the shields have to be electrically connected to a conductor of known potential. As long as that happens, there is no problem. So you are kind of inside the insulator, you are kind of forcing the potential to a certain level, and you're along the insulator. As a result, the stress becomes better graded, and you don't have high field gradients. But what can happen is that over a long period of time, the contact can wear off. There might be damage to the contact, there might be contamination, and as a result, over time, the electrical contact with any of the fixed potential surfaces might be lost. So then you have a shield which is neither earthed nor held at a particular potential, so it will acquire whatever potential according to its geometrical arrangement, according to the geometrical configuration. And so therefore you have a shield which is at a floating potential. When you have a floating potential, if you have a metallic component at a floating potential, partial discharge can occur between this component and any neighboring conductors. In the early stages, the PD will be very small and it will come and go, so it may not be possible to detect that. But given a small amount of time, the floating component discharges become pretty large, and therefore they are very easy, comparatively easier to detect either through electrical measurements or acoustic measurements. This is important because PD at floating components can be quite hazardous and very likely to cause very quick failure. Within a matter of minutes to days, it can cause failure. Another problem is that even if it doesn't cause failure, if you have continuous discharges happening between the floating shields and the conductors, there would be continuous decomposition of the SF6 gas. And the resultant byproducts might be corrosive, and they might chemically attack the components, the materials around it, and may drive that insulation to failure through a secondary mechanism. In severe cases, discharging will also cause more metallic particles to be generated. So there will be some kind of erosion or bombardment, and as a result, your metallic contacts may actually crumble, and they may produce a lot of powdery substance. So these metallic particles then in their turn will continue to produce discharge and hopping excursions, and they will acquire charge and cause partial discharge. So this is one PD that we can quite well control. Now, every time I keep on talking about electrical and acoustical detection, we should remember from our discussion on partial discharges that acoustic detection came into vogue particularly in response to the requirements of gas-insulated substations. We had Graybill who had done some pioneering work. Apart from that, we also have insulator defects, where you have small manufacturing defects which probably were not observed during quality control. Even while in preliminary testing, they did not cause problems. This could be like voids or embedded metallic particles. Generally, the partial discharges from such defects will be small. However, over a long time in service, they can cause failure. But they are difficult to trace at the stage where we can take corrective action. You can have other internal defects also, like internal metallic contamination in solid insulating structure, embedded metallic particles, or protrusions on the conductor. All these can cause premature failure. They will cause PD, but this PD may not be very easy to detect or locate at the stage where we can take corrective action. Some can be done. So PD resulting from such defects may be extremely difficult, extremely small, and nearly impossible to detect until some seconds to minutes prior to failure. So the only thing that we can do is we can ask the manufacturer to be more careful and to control the presence of such defects at the preliminary stage. Thankfully, in modern design, such defects are rare, and we are moving to a situation where we don't have to worry too much about this. Especially when you have PD inside insulators, there will be considerable attenuation of the signal, the acoustic signal, before it arrives at the enclosure where you can put up the sensors, acoustic sensors. So let us therefore discuss a little more formally about the various partial discharge measurement techniques that are used in gas insulated substation. The first is, of course, the electrical method. The partial discharge will produce a signal which is about very small duration, so it'll be about in the nanosecond range. Now, the coaxial design of the GIS can support high-frequency signals. Therefore, even if you have small PD, it should be possible to detect the PD pulses with a high amount of fidelity. But you should remember that both issues are there. One is that of attenuation. So, as it travels along the path that it travels and the distance of the path from the source to the sensor can cause considerable attenuation. Also, there can be considerable dispersion. That is, the very different frequencies will travel at different speeds, and therefore the detected signal at the sensor will be considerably different from the signal at the source site. So, electrical detection is possible, but it has its limitations in case when you are using it for GIS. Conventional PD measurements use a reduced bandwidth of about 100 kilohertz. Now, instead of using measurements at this ranges, one more possibility is to use ultra-high frequency sensors, because you would have a better signal to noise ratio and you would have you can have higher sensitivity if you perform measurements using ultra-high frequency method, which means we are operating at frequencies of 1000 megahertz or more. So when we go beyond that range, it is called UHF detection. But then we also have the problem that the PD signal is an impact signal, so it has the entire frequency range, and we decide which will give us a better signal to noise ratio, which will have less noise, so we choose ultra high frequency range. But then again, even though there will be less contamination at high frequencies, the fact remains that the highest frequency components are also going to suffer the maximum propagation loss. So by the time it reaches the sensors, there might be considerable attenuation. UHF methods therefore may be limited to cases where the sensor is in close proximity to the defect source. So typically, if we expect the sensors to be within 10 to 20 meters of the source, we can expect the UHF method to work. Sometimes we don't go to that high frequencies. We still work with UHF frequency, but we use a reduced frequency range, so maybe a few hundred megahertz. This offers a good compromise between sensitivity and sensor placement. So when we know that we are likely to be at a considerable distance away from the source, the sensor will be placed at do not have access to very close to the source location. We may not go to that high frequencies, but we come to 100 megahertz or somewhere in between. So we are still in the high frequency regime. So therefore we do not expect too much contamination by noise. And at the same time, since these are not the highest frequencies, therefore the attenuation, the losses, propagation losses will also be lower. So essentially, we have to decide what frequencies to use, where to place the sensor, and all these needs engineering judgment. You may also need to use sensors which are specially adapted to the gas insulated substation. Next, of course, we have acoustic methods where at the source of the PD, acoustic energy is released. These acoustic waves travel through the SFC's gas and they reach the GIS enclosure. At the GIS enclosure, the metal begins to vibrate, and if you place acceleration sensors or accelerometers or displacement sensors on the outside of the GIS enclosure, they can pick up the small vibrations of the enclosure. So discharges occurring within the solid insulation inside a GIS are very difficult to detect because the acoustic signal will have to propagate not through SF gas but through the solid materials, and therefore there will be some solids might be opaque to acoustic waves, so they will not block the acoustic waves, they will not allow acoustic waves even to travel through, or there might be considerable attenuation. In case of acoustic emission, again, the best kind of PD inducing defects that acoustic methods can best detect are the metallic particle contamination. So when you have signals due to metallic particles jumping, lifting off, and then bouncing on the enclosure, and then PD happening, those kinds of discharges are best measured, best detected through acoustic methods. Apart from that, we also have chemical techniques. When partial discharges occur in the SF6 gas, the gas will decompose and they will generate byproducts. So in a manner similar to the dissolved gas analysis that we have discussed in the context of transformers, we can use chemical techniques where you try to figure out what is the percentage of a particular byproduct within the gas. So again, you would have some kind of gas extraction means, and then you would need some chromatographs. So as the rate of production of the byproducts is very small compared to, let's say, in a transformer, you cannot use this as a continuous, you cannot use this as a short-term testing tool. You will have to wait, you will have to let the discharges continue over time, and over a long period of time these byproducts need to accumulate, only then they can be detected. So an extended period of time, weeks, months or years, is required to provide measurable results. When we are talking about the SF6 byproducts, these are the different kinds of byproducts that you would expect. SOF2, SO2F2, SO2. These are thionyl fluoride, sulfuryl fluoride, and sulfur dioxide. These are the various percentages that you would be interested in. When we talk about testing of GIS, firstly, of course, they have to undergo dielectric test. Apart from dielectric test, there are a whole range of tests that are important, that are pertinent in the context of GIS. Some of these are measurement of the resistance of main circuits, temperature rise test, short time withstand current test, peak withstand current test, verification of the degree of protection of the enclosure, the tightness test, because we need to maintain pressure, electromagnetic compatibility test for safety of equipment and personnel outside, verification of making and breaking capacitors, low and high temperature test, proof test for enclosure, pressure test on partition, test to prove performance under thermal cycling and gas tightness tests on insulators, circuit breaker design test, fault making capability of high-speed grounding switch, switch operating mechanical life test. So there are a whole lot of tests that need to be done. These are generally type tests. There are routine tests which also need to be done. If we look at the dielectric test, the most important, the principal dielectric tests that we need to do on gas insulated substations are power frequency tests. Power frequency test should simulate conditions under operating frequency and test for the various kinds of dielectric withstands. Lightning and impulse test, for which we would need to simulate atmospheric overvoltages. We know what kind of voltages to expect, what are the IC test standards. Switching impulse test, simulating overvoltages caused by switching operations, PD test. There is a whole range of PD tests, and it also forms a part of the online condition monitoring of the system. This PD tests are done to ensure that the design and the solid insulation is free of partial discharges at all times. And then you would have to have tests on auxiliary and control circuits, which will verify that the insulation of the auxiliary and control circuits withstand dielectric conditions. This will be mainly done on secondary circuits, and all these first tests will be done on the primary equipment. So all in all, gas-insulated substations are a considerable improvement over air-insulated substations. They come with a lot of advantages, but they're much more expensive, much more difficult to build. But at the same time, once it is in place, we have to bother less about it. They do not need so much periodic maintenance. They have better life, but there are issues connected with them as well. A lot of research is geared towards condition monitoring of GIS through PD monitoring. So these are the references that I have used for the lecture on gas-insulated substations.